So we are doing testing implementation, right? It is testing implementation. I mean, then okay, let's say if you reduce the size, how we can reach for the same size or some other size. Okay, so we need some interpolation. We discussed two methods of interpolation. One was that one, right? Yes. Yes. So we just in this number, we just don't do anything but just replicate them, okay, to nearest point. And then the bilinear, that's why it's called bilinear because we first add into rows and then in the columns. That's why it's called bilinear. After we have the equation, if you want to do the equation or directly something. So you will also see the effect of these two. Let's say you have a picture. We want to enlarge this picture by a factor of 4. So it means what we are trying to do is we insert 4 pixels inside. So we need it to a factor of 4. Okay. So let's see the effect of these two, the bilinear and the nearest neighbor. So let's focus on the, because if I just enlarge this whole picture, I may not be able to see the effect. So I have to zoom in. So let's zoom into the face of the parent. Now here you see one method I applied pixel application, the other method I applied bilinear, and it's very clear that this performs better than this because here you can see some dots. Okay, so this is like the effect of the interpolation. And if we zoom in more, you can see that it's very smooth, not smooth. It's very smooth. Yes, because it's like we are taking the mean of the neighborhoods. This we will discuss this later again when we will discuss the filtering. So this whole script I just prepared for you guys to basically see how the same things are done into the MATLAB and the other stuff. Okay. In order definitely, as this course requires some understanding of the program, so I will not go and give you all the details, but I can give you the hints, okay, that you can apply. So here I am reading an image, okay, which is a peacock image. Okay, it's already built in the MATLAB. So if you read it, it will display you the peacock image. Okay. Then what I'm doing is I'm doing some undersampling or I'm reducing the samples. Okay, which we already have seen. We are reducing the size of the image. So how I can reduce the size of the image? If I have some background of the programming, when we upload an image, basically that image is what? A matrix. So it means that if I have rows and columns, in order to reduce the size, I have to select some rows, drop some rows. Okay, and similarly for the columns. So if you are somehow familiar, these are the rows. So I selected first. Then after first I dropped 5 and selected sequentially 4. So I dropped 5. So 1 and then 6 and like this one. So it means that I'm reducing by a factor of 5, right? Reducing this number, okay? Similarly, rows and then the columns. Okay, 1 to 5, I drop 5 columns and take that one. So it means that this will reduce the size of the image by 5. And there's also third dimension. What is that? Color. Okay, because here the peacock image is a color image, so we have rows, columns, and then three colors. Okay, so it will be 3. So, but I have to take 3 all of them just to make sure. Okay, so this is like undersampling, and you can downsampling or undersampling, you can say that. And the original image was this. You can divide by 5 to get the undersampled or downsampled image. Okay, so this is like the sampling itself. Okay, so this is the first thing. Right now, let's suppose I have to reduce whatever the quantization size is. Let's say I want to reduce the quantization level. Okay. Originally it will be 255, 255. I want to reduce it to 64. Okay. You see what I'm saying? I'm doing sampling and quantization. So first sampling I did. What I did, I just tried to reduce the sampling just to show you that how the samples are, how to reduce the sample or improve the sample, right? Then I'm trying to reduce the quantization itself. So what is in I, which is the image, this shows the amplitudes, which are from 0 to 255. So what I will do, I will normalize by 255. It will give me from 0 to 1. When I divide by 2, it will give me 0 to 1. And then I multiply with
63.
It means that it will go from 0 to
63.
So I just, okay. So I reduce the number of bits, 6 bits instead of 8 bits. Okay. If the same image I want to restore it, I have to apply interpolation. So fine. So this is Python code. The same thing is there. Only the reading and syntax is part different. Okay. So here we need some libraries for Python. Okay. Here you see I am read. Here I just use read. I am read. Here I am using the package with the I am read. Okay. So just the syntax is different. The same image I am uploading. Here again I have to do the same thing which I was doing here, but here I have to write 1, 5, 9. But here only the syntax is different. Here the brackets are different. The other things are different. So if you are familiar with one, you can do the other. Okay. And nowadays, by the way, the good thing is with AI, if you have code in MATLAB, you can convert it in Python by just okay. You can also convert Python. Okay. So it's just reading the assignments, but it's it's up to you if you want to read it because that's all the things are still relevant. They just put it without anything. So I just pick the things that are important and I give more example in order to understand. So in this set of slides, what we did basically, we mostly just talk about the sampling, quantization, and acquisition. Okay, and this was the main. Now after this lecture, we have an image. What is the image for us? It's just a set of pixels with rows and columns, and each pixel has a value from 0 to 55 or any number that is integer. Okay, and all the values are integer. So for us now, the image is just a set of numbers, integers. Okay, and now we have to tell it. Okay, now we will see some of them. Okay, first was this one. We did the acquisition in the first slide. Now we are here. Now we come to the special domain. Why is it called special domain, not the family domain? What is the difference between special and family? Yeah, we also sometimes quantize the signal, and we only time domain, not the special domain. So the thing is that if you see the image, there's no time information in it. Is there? No. There are pixels that are arranged in a some spatial space in the distance, right? So that's why we call spatial domain, not the time domain. Okay, and if you talk about the signal, most of the signals are relative with the time. Okay, so now here you see some operations, arithmetic operations, pixel-wise operation, and this is again a physics, and most of them we will discuss in the coming set of slides that in more detail. Okay,
When we say quantization, can you simplify say image sampling and quantization?
yeah, acquisition can also contain the capturing of the image, the whole assembly, but sampling and quantization is a part of the process. So that's why we focus more on the sampling and quantization, not actually applying. So if you remember, we just talked about that there's a set of sensors that capture different frequencies, and then from here we get different type of images. So that's enough for us because we're not doing acquisition more. Okay. Yes, that's acquisition part. Let's move on. So in this set of slides, I will be covering some operations like some arithmetic operations, pixel-wise, and also we'll see some random variables or see the intensity as a random variable, which will help us finding some methods later on or crafting some methods. Okay, so it's very simple. If you want to add two images, okay, it will be just a simple addition. But addition, how you add them, like point to point. Okay, each pixel is only added to the point. Similarly, subtraction, we can subtract them, we can multiply them. So multiplication, what do we do multiplication? Multiplication of it's basically two matrices, right? So if I multiply two matrices, what I will get? I have to do the row with column. But in images, when we say multiplication, it's point to point multiplication. Then each point will be multiplied with another point. I will give you an example. Yes, dot multiplication. Yes. Similarly, division, it will be point to pixel-wise division. Okay. But one thing we have to make sure that when we are adding, dividing, or multiplying, since we are doing point to point, the size of them should be same. Okay. And if it is not same, what should we do? Yeah, we can do multiplication. Yes. We can reduce the size of other. Yeah, this is called padding of the image. So I will pad them from the outside. Okay, and there's a method for that as well. So these are the methods just to make it. Padding is like you add some views outside the image. Okay, let's say you have 2 by 2 image, and you want to, and there's another image which is 3 by 3. Okay, so in order to add, what should I do? Yeah, so I have to add views here to make equal, and then I can add. Okay, so these are different methods. So now the problem is that if I add 2 images, okay, both are from 0 to 55 to 0. What will be the resultant image? It will be from 0 to 512. Okay, similarly, if I want to subtract, the difference image will go from this minus 255 to 55, right? Yes or no? Okay, so what again? Whenever I'm processing the image, I have to make sure at each stage that it is from 0 to 255 or 0 to whatever level I define it. Okay, so in order to convert it back, one way is to set all the values less than 0 equals to 0, greater than 255 is equal to 255. But this is like cutting off. I'm losing the information. Okay, clipping off. The full range of information not captured. Any full information I will not capture it. So one way is to basically normalize it again to 0 to 255. Okay, so how to do that? First, I have to subtract the image from the minimum of that. When I will do that, I will make sure that the minimum of the image becomes 0. Okay, if I subtract from the minimum, it will make the image go to the
positive
level. Okay, and then I divide with the maximum and multiply with the case like 255 here, whatever the maximum, it will give us from 0 to 255. Yes or no? Okay, so this is called normalization. So whenever we do something, okay, we have to make sure that the values are within the range. That is scale. Okay, and we can do the same 2 steps in 1 step, right? Just minus minimum divided by max minus minimum into gain. This is the formula that will give you the same thing that we did it in this. Okay. So let's see. Yeah. So here, yeah. Again, as I said, this is the point-to-point multiplication, not like the matrix multiplication where you just multiply row with column. Okay, that's clear. Okay, fine. This is just an example, very dry example, I will say, not that fancy example. If I want to add 2 images, I will just add point to point. I'll get 0 to the values become 0 to 5 by 2. So I have to again apply the normalization or the scaling for each point, and I will get from 0 to 55. And at the last, since I need the integers, I have to round it off to get the integers, right? Okay. Okay, this is the division. Again, division doesn't mean that you have to divide the 2 matrices. It's like point to point division. After that, I have to normalize, and after normalization, this is the final result after rounding it off. Okay, so I think this is just a simple example. Okay, now the application. Okay, let me give you an example. Let's say you have a security camera stored in one place. Okay, and there's some distortion, maybe some dust. Okay, that is moving. Of course, dust will not stay at one point. It has to go like this, right? Okay, and if my security camera is recording like every second and every minute, okay, let's say you have 60 frames per second, and if I take for each second I take one picture. Okay, for some minutes, for maybe for 5 minutes. So what do you think? What will be constant in that images, and what will not be a constant in that images? So that scene itself on the background will be a constant because it's a security camera. But what is not constant is that this is dust. Okay, so if I take let's say 100 of these images per second, okay, and I add them and divide by take average. Okay, so what I will get?
It's not like slow motion, slow photography on the screen where the cars have only
yeah, that's what I'm saying. The scene is constant because the security camera, when the scene is constant. Okay, so that's its formula. I am just doing stacking as you mentioned, stacking adding divided by total number of the images, which is actually the mean of that. So if you get the idea, it will enhance the image and it will remove the dust. Why? So the question is why? So it's simple technique. I'm just taking images, adding them, divide by the total number, or even if I don't divide by the total number, I just add them and do the normalization. Okay, it will enhance the image and reduce the dust. So if let's say it's dust particle is here in the next string is there, okay, if I'm adding it, I'm just reducing the dust effect. You see what I'm saying? You get my point now? So this is a very basic method for remarking.
I was noise of dust reduced except that I'm happy with positions.
Yeah, assuming that it's moving. Sometimes so it will not, yeah, it's a random particle, and sometimes it's like in some pixels, the other is other pixels, and add them, the result will be reduced. So similarly, any noise, this is just an example. Let's say you have images that has random noise, and I will show you example again, it's a MATLAB code. So if you have images with the random noise, you add them, the random noise will go away. Yes, so that's true. Okay, so by the way, this is again an accident idea. Let's say I want to highlight a car passing or something. So let's say I subtract two images. So I get, if I in one image the man is there, in other image the man is not there. So if I subtract them, what I will get? The man himself, right? So you see the power of this plus and minus. It's just plus and minus, but however in images it's like very powerful. Yes, that's you have to. That's really important. Because noise, okay, and noise not only model. Okay, anyways, don't confuse yourself. Just for timing, add it and reduce the noise. Is that clear? Okay, fine. So even statistically, I can say that. What was actually mathematically, I can say I have an image, right? Each pixel with some noise value, right? Some any random value. Yes or no? So if I take the mean of that, this is a constant thing, and this is a variable thing. You can assume it to be Gaussian with zero mean. So if I take the mean of that, mean of g of xy will be what? Mean of this plus mean of this will be zero because we assume it to be zero. Because every time a random variable, we can assume it to be zero. Even if it's not zero, if it is a number, it will be just a number, right? So it will just shift the image with something. It's not a big issue. So what about the mean of a static variable or deterministic variable? It will be itself, right? Because the static, just a number, right? So if I take the mean, which I'm taking it, I'm adding that, right? So if I take the mean, I will get this will be just a number or a zero. Okay, so statistically, if I take the mean, I'll get this. Yes or no? Okay. This one? This is just in our case, it is in unit is a noise. Okay. Okay. Here, what I did is the same thing that what I said. Okay, I have an image. Okay, and this is the color. I just converted it to the black and white image. Okay, and then I added a noise. This is a random noise. By the way, the same thing you can do it with. Okay, before that, in MATLAB, you just upload the image, add ran is a function. Do you know the ran function? Yes or no? Yes. Ran is just a noise. Okay, random function. Add that random function to your image. Okay, generate at least 100 samples of this. Okay, 100 samples. Add to the images, and then after that, add all images. You will see that right here. Here I took 1,000 samples of the noise, and I assume it to be Gaussian. Okay, then after that, I took the mean of this I is the image. I added the Gaussian noise to it. Okay, 1,000 I generated 1,000 images, and then took the mean. Okay, in 3D, and then I just run this code or the same code here. Also, I generated a noise. Okay, added to the images, 1,000 images, then calculated the mean, and after that, I just displayed them. Okay, so again, one example we have seen that addition will help you in reducing the noise, and sometimes in order to compare two images, I can subtract them like error. So the subtraction is good when I'm comparing. So what is error? One quantity minus the other quantity, whatever. So if I subtract them, I can find what is the error. Like here, we have the different printing quality. So in order to see the difference, I can subtract them and just find out that how much is the difference between the two images. Okay, which is a kind of error. Similarly, here sometimes in in medical images, let's say you have a reference image, a healthy person image, X-ray or MRI. The other is some other patient image which you don't know maybe healthy or not healthy. So what I will do, I will take this one, subtract the other one, okay, and try to find some problems if there is any. Okay, so this is again very, I will say, easy technique and can be done. Now here, what about the division? Division again, see, let's say I have this image, there is some shade. Okay, let's say I know this shade is this. Let's say I have some way of finding what this shade is. So if I divide this by this, I will get the theme image. It depends on the phenomena itself. It's multiplicative or additive. In their noise, we assume it to be additive, which was making sense when we are combining them. Assume that this is this process which happens to be due to multiplication, and now you have to divide it to get that. Okay. Yes. Okay, so we discuss some arithmetic operations. Then there's another way. In this set of lines, basically we are doing some derivatives. Okay, the addition, subtraction that we discussed, and some application together with some other. Now here, not linear versus non-linear operation. Now, if I'm applying some operation on an image that is linear, then I can somehow make my calculation easy. If it is linear, okay. If it is not linear, then of course I cannot make my calculation very easy. So, what it means? What is a linear quantity? You know about this, linearity and homogeneity property, right? So if the operation, any operation, is basically satisfy this one, then it means that it is a linear quantity. Okay, so what is mean by additive? Any operation on this separately, or if I add them and then apply, this should be equal. This is additive property. Homogeneity is if I multiply with A and multiply with B, this should be equal to this. Okay, so this is, in other words, this whole equation defines it to be what? To be the linear. Now let's say I multiply two images. Does it mean it's a linear operation or non-linear operation? You basically prove it by this equation. Is it not linear or not? Multiplication of two. No, this one that make logic of it. Like I just try from this equation explain to me. Okay. Right. Okay. So here, fine, it's not, but let me explain to you. I said a multiplication operation. So this H is actually a multiplication. Okay, in our example. Okay, so let's take an example in which I am applying the multiplication of this image by itself. Okay, I multiply this for this. So if I multiply this, means that this function is what it will be. So here it will be what? A multiplied by f1. I multiply image by itself. It means that I multiply point to point, right? So it will be square. Okay, and plus b f2 square xy, right? Yes. Then I take this one and apply the multiplication on this whole. So it means that a f xy, okay, plus b f2 xy and whole square. Is this equal? No, it's not equal. Yes. So it means that if I wanted to multiply two images, I have to do it separately. They are not same. Because what's the benefit of this? What is the benefit of linearity? Because if I wanted to apply some operation on this and on this, it's better to not to do this, but to do this if the operation is linear. Because here I'm doing twice, here I'm just doing once. Right? In order to save the equations, calculations, I have to just apply the label. That will be suitable if you have the operation is such a linear operation. Now we just move towards we did some arithmetic operations, and now let's move to special operations. So it can be the special operations can be single pixel operation in which I manipulate each pixel separately, okay, without caring about the other pixels. Okay, this step. Okay, the second is the neighborhood operation in which I take a portion of the neighborhood of the pixel and try to basically manipulate it. Okay, and then we have a geometric special in which I try to rotate the image, whole image or something like that. Okay, so let's okay, fine. Now one of the single pixel operation, some of the single pixel operations are shown here. Okay, so you have, let's say z is the original pixel, and I transform that z to some other pixel which is called s. Okay, so one of them is this called the negative. Negative means that what I did is I took a pixel and changed the value, okay, for 0 to 255, and if it's 255, change it to 0, like invert it. Okay, so this is called the negative, and again this has an application in medical especially, because sometimes medical images are like confusing. If you change it, it will start showing some other things that doctor wants to see. Okay, this again, this is your original image pixels, and you want to change it to something else. Okay, so this curve defines, let's say I have to map, if the pixel is here, its value should change to some other value in this location, right? What is the benefit of this one? I'm mapping. I'm doing this for a single pixel operation. I'm mapping or changing the pixel, each pixel to another something else. So first, what I did, this is negative. I created a negative of the image.
So every pixel is just minus 255.
Yes. Yes. Okay. Now here it's a mapping based on this curve. So I have to find out. Let's say my pixel is in the middle. Let's say 100. So 100. Let's say this is 255. 0 to 255. 100 will be here. I have to see what it should be changed. So I have to map from here. Let's see here.
It's not uniform.
No, it's not uniform. Of course. Yes.
Okay. This one is just.
Let's say it's 255. Okay, it's 0. Fine. So I have to find. Let's say one of the pixels is at here 100. So I have to map it where it will be. Maybe it goes to 90, something like that. What is here at the lower side? Black. What is here? White. Okay. So basically, what I'm doing, I'm trying to separate them, moving back towards more black and white towards more white. Okay. So it will, yeah, the texture should make visible. Okay. I will give you an example, and it will be on the real image. It's a mapping. As I mentioned, you should have this curve or equations for this curve in order to do that. Lookup table. Yeah, definitely, if I'm saying this, it means a lookup table. It means that this intensity will be mapped. The darker will become more darker, the lighter will become more lighter. Okay, so it will enhance the image because it's the dark and light will be more separated. These are the values. 0 to 255 are the values of the pixels. And if let's say in the image I have equals 2, I have to map 2 to the other side. Okay, what about this? Okay. Yeah, so I have k. Let's say I set k equal to 100. So it means that above 100 I make it the high, and look, so it becomes black and white. And this is somehow in the middle. Yeah. Okay, so it will not be black and white, but it will separate the black and white more to make the image more clear. Okay. No, it's not smooth. It will be more. I will say the texture will be clear more. Okay, so here again, simple example. A negative is separate from 255, so I will get the negative. And if I want the thresholding, so I can just, let's say the threshold is 97, so above 97 will be 1 and below will be 0. But depends. Sometimes you can say not 1 but 255 to 255. Okay. But at the same time, now what about this? Either we can do it by lookup table or the graph. If you have a proper graph that can show you like MATLAB graph that can show you that what you can use it. Or if you are doing a paper, the best is to find the equation, which for this is very difficult, but definitely we consider some simple case. Let's say let me give you an example. Let's say I say this and this. Can I do equation for that? Linear is just a straight line equation, but again, the example will come up in the later slide. Now see. So what is the effect of that? This is complement, definitely it's one of the application can be in the filters that we have in the mobile. Sometimes you want to take the negative, right? But its application is mostly in the medical field. There are sometimes you want to hold that image in order to see some details which is not visible. Okay. Then thresholding, again, this is becoming black and white. Again, this thing again is suitable when you are doing some segmentation. Okay, like here you can easily say segment the actual with the background. You segment it, right? Similarly, contrast is stretching. The middle one is actually, as I mentioned, is we are stretching it, and you see the beauty. This is very blurry or very white. This becomes much more bright, right? So, what we need is separate the positive and negative points. Yes or no?
No, it's not the picture like some of these social media applications. When you talk, they put like a mask on your face. Or
Yes.
So this thing, they are just.
They are pixels. They're mapping the pixels. As you mentioned, yes. Like I take the face and want to put your face on other. It's like the pixels space. And you can put it by yourself easily. Okay, but then it requires some programming skills. Now, this was a pixel wise. We are doing each pixel learning, so it's without considering the outside. So another operation in which we take, instead of the one pixel, we take the neighborhood of the pixel. And one of that example is if we just take a box, okay, inside box, let's say we are taking the mean of that pixel. Okay, so what I will do, this is like image. I take a box, okay, take the mean of that, and then take
a group of pixels.
Yeah, so I take this group of pixels and take the mean. Then again, in order to do for all the other image, I have to move sample by sample. Another sample, another block of same size, take the mean, and do it for each row and each column.
Overlapping the
Okay, so you see here, this is original, this is now blurry, but definitely here we cannot see why we blurred it, but we'll see it later on once we have some verifications. Okay, now let's see the box size is 3 by 3. The box size I said it is 3 by 3. How I can apply here? So this, okay, what is the consequences of applying this box and reading all this? First one is no, it should not reduce. After doing this, but we get a blurry image. Okay, the ball we get up if I want to be positive, but I get okay. Smooth image, right? So this again, you see, smoothing that here you see, the edges are very clear, right? But here it's very smooth, right? Now, what is the effect of this smoothness? Again, it goes back to what we said for the noise. Previously, we gave an example of noise, right? So we said we have series of images and we have different noise and we add them to reduce the noise. But what if I have just one image, and it has a noise? So I can take a portion, take the average, smooth the image and reduce the noise. Previously, we are taking averages, now I'm getting the image and taking the various portion off. So this is what but this is called the filtering that we'll discuss again in detail. But this is for just to show that what are the neighborhood operations that we can have. Okay? Here, yes. Of course, there will be consequences. For this type of filtering, you have to do, let's say, here you lose the information. However, there are other ways to do it, to recover it. What I can do is, if I just take the edges from here and try somehow doing some operation, try to add that edges to here. There are always some of the other operations that it's not performed just independently. You should have some other operation. We will see. So let's say we have 3 by 3 block here. So how I can smooth this image by 3 block? From here, I have to start. Yeah, or okay. So I have to start from the first. Okay. Did you notice that whenever I'm doing some operation, it should be odd numbers or even numbers? Let's say here I started with 3 by 3. Why not 2 by 3? Even if here, why we have odd?
These are pixels.
Yeah, these are pixels.
So why they have to be?
Not here. The size of the box here, size of the box that I this 3 by 3 is the size of the box.
That is it.
That I select. Okay. So and I will select the box. Okay. And inside the box I will average it. So this is the image. Although this is like coincident, this is also 3 by 3, but it doesn't mean that this 3 by 3 is same as this 3 by 3. 3 by 3 is the box I want to select. Okay. So now I have to apply that box to each filter. Okay. So how to do that? Yes. So what I will do, I will start with this one. So since I have a 3 by 3 box, so I can, 3 by 3 box, I can have it here.
This is the box I have selected. This is the original picture.
Yes. This is the box I selected, and all these boxes, the inside of this, I have to average it. Okay, but I have to make sure that the size of the image should not be changed.
So you don't have this in the original image, just say 50 by 50, and you selected 3 by 3. So you are saying why I selected all 3 by 3, 5 by 5.
Yeah, this is my question. So let's say you have to, now 3 by 3 I selected this, the outside I just selected it to be 0. So what will be this result of that? The sum, right? Divided by 9, which is equal to 20. Fine. Now after that, shift it to another. So again, I moved it this one to this one. Okay, done this. Now I have to add 10, 50, 80 plus this and divide by 9. Okay, now the third one will be again here. Okay, and this will be zeros and again. Now after these three give me these numbers. If it is fractional, it means I have to round it out. Okay, now after that, what I have to do? Second row. Okay, so I will move it to another row, which is this one, right? Okay. So whatever is the middle is my pixel position. The middle one is my position which I have to fill it. Okay, that's why it's odd. If it is even, then I cannot have a middle position. It's not necessary that you should not do it even. You can do it. Okay, you can have a set of rules. Like let's say if I'm doing this is my original pixel, like whatever I will get it, I will put it in this position. So in the last topic, we try to manipulate pixels, right? Let's say I want to move image left, right, or rotate it. Okay, yeah. So this is called the geometric transformation. So if you have an x-axis, 0 start from 0, I want to move it to some other place. So what geometric transformation will look like? The transformation of geometric will have a general form of this. What is x and y? X and y is the position of the pixel. Previously we were talking about the pixel itself. So now I'm not changing the pixel. Previously I was changing the intensity, but now I'm not changing the intensity, but I'm changing the location because I'm shifting it or stretching it. Okay, so I'm therefore intensity will not change. The x and y location will be multiplied with this matrix to get a new location. Okay, now you might be wondering why this is there. Okay, let's see. I have x and y pixel, x and y. Okay, and I just need a 2 by 2 matrix, right? And that should give me another one, right? Makes sense. I just multiply based on that numbers. Either the pixel will be shifted or not. I will just show you that how to complete these numbers. Okay, but why we have this row? Why should I multiply with the intensity? This is not intensity. I did not multiply. A11 is just a number. This is not intensity. This is just a number. I will show you what this means. It is a general form of geometry. General form. Okay, what they are? Let's go there. See, let's say the same matrix here is 1 1 1 0 0 0 0. Then your diagonal matrix. What it will do to the image? Nothing. Just an example. If I multiply, let's say I just take this one. Okay, just this one. This also one. Already one. This is 0. So this is an identity matrix. I am not doing anything, right? And this like I'm going to give you an overview that how it works. But let's say if I have this a positive number and this is 1. So what it will be? This is a positive number, this is a positive number, any number. And then 1, these are zeros. If I do that, it means that if I apply that equation, I will get this. It means that I am scaling it. So if I scale, what it will be? I am just stretching x and y, right? So what I did, see this was the original, what I did. There was x which was 1. Now multiply with cx which is let's say 2 or something. So it means that I shift 1 to 2. I basically multiply with the scaling factor to stretch it in this manner. Okay. Now here, see if I just use some constant sign, which is a tilting of that. If I use these values, definitely if I multiply this metric with this one, I will get this equations, and this the theta will define the rotation. You see this? I am just adding some constant number, so I'm not actually stretching it, but shifting it. Okay. Similarly here, if I add x and y and with some constant number, actually I am just playing with this. Okay, and these are, if you saw nowadays, very easy to find the application because all these filters that we have in the mobile is like based on these things. So sometimes your face becomes big or small, and this is because of this, right?
This. What's one in the mix? Is that x size y is the way, but what's one?
Yeah, one actually, this case, even if you don't consider it, there's nothing. But why one is there? Because of this. As I mentioned, this is a general form of all these transformations. So in order to generalize it, we have to put this thing. Because if that is not there, the matrix size will not be different. You know what I'm saying? So because of this, I just put 0 0 1. If you're not considering this case, otherwise it's matrix.
Yeah, how did we enlarge?
I'm stretching the location. First it was between 0 and 10. I stretch it to 0 to 20. You see what I'm saying? Okay, so if I stretch it because I multiply with this, so if the pixel rate is 0, it will remain at 0. But if the pixel rate is 2, if the cx is let's say 3, so it will become 6.